All right. Everyone, June 13th. All right, so we're gonna do this first. And then we have a lot of different methods to try for this. I can do this. I don't know what this is. I can do this. No, this is a different thing. So yeah, we're gonna do at least two methods. Okay, two methods. One is sorted list. We know what it is. Yeah, we do sorted list. And the other is DSU. So we go both on that. And if we still have time, we're going to look at the sweep line. Okay, minimum absolute difference in binary search tree. The minimum absolute difference between the values of any two different nodes. All right, it's a binary search tree, so all we need to do is to traverse it from in order. Is that what they call it? In order? Left to right. So we traverse left to right and find the adjacent, right? Because that is the minimum absolute difference. You have to find the adjacent. Okay. Oh, hold a second. Did we set up the? I don't think we set up this. Yeah, I didn't use this yesterday. I don't think we use it today either. But let's set it up just in case. What do you think? And we're gonna traverse it, right? So traverse it, we'll visit left. Right after finishing visiting left, we get the left value. And we have a result, a global result. And we say DFS. And we got in order. Okay, in order. We have a node. And then we don't return anything. Or we return something. We can. What if we return the minimum in this subtree? Right? What if we return the minimum in this subtree? That's an interesting thought. Hold that thought. Let's try it. What if we return something? Anyway, if not node, we'll return math.inf. That should be fine. Otherwise, we'll say left min, right, equal to in order. So we always go left, and then we're gonna say right min in order node.right, and I'm gonna return the minimum of left min, right min, and okay. Okay, I don't think that's the right way. We're gonna say if left, if right, because I want to know the difference between me and my left and me and my right. So I need to know if the left is good, right? That's fine. So we do that, and then we say current min. Current min equals to node.val. Okay. ABS. Node.val minus node.left.val if node.left, else math.inf. Right, so that's that. So I'm going to minimum of this and this. That should be right. Okay, so when we're done, we're going to say current min. and then we just need to return in order root. Okay, let's take a look. Looks good. I mean, edge case is 2. Let's try 2. Root is not valid, of course, because that's, yeah, it should be 1 0. My bad. It should be 1 0. Alright, give it a run. Oh my god, I was wrong. What? What is this? Expected 9. Oh, binary search tree. Oh my god. Ah, it's not this. Okay, I was very wrong. Understanding of binary search tree is wrong. This, yeah, whatnot. Okay, I need to return different things. Okay, now I need this. I need to return the largest one for the left subtree and the smallest one on the right subtree. Man, we're visiting these values, right? We're visiting this value. Now I don't want to pull it out. How about we return min max? Right? We can return min max. For each subtree, we return min and max. Okay, we'll return min max. Nah, still, I don't want to do this one. So, min max, min and max. Doesn't matter. They both can do inf. Okay. Then left min, left max. And I can say L min, L max. How about that? L min, L max. R min, R max. Right? And then current. No, I do need self-dom results. Ah, jeez, man. That's okay. So what we're gonna do is self.res equals to minimum, right? Self.res and then node.val minus left max. And right min minus node.val. Once we're done, min will be node.val and no, we want the minimum value. Yes, the minimum value of the subtree. This is the minimum value of the subtree. And we also want a max value of the subtree. But isn't the max value of the subtree yeah, it should be right max and node.val. And here we shall change because if it's only a single one, right? If it's a single one, if it is a single one, then we need to make sure that the minimum and the maximum should be this, right? And then these shall all be ABS, just in case. I'll return self.res. Okay, let's give this a shot. It is right. What was wrong? Something is wrong. something is not right. I mean, this is 2 value. Okay, that's fine. We can do tuple on this. Oh, there's no left. There's no right. Inf is not valid for the expected return. Oh, we get an inf. Left min, left max, right min, right max. So I shall be able to get the right value out. What the hell? Yeah, not null. This should be infinite, negative infinite, infinite, negative infinite. Yeah, this is not right. No, that's fine. This is all infinite, so this will be infinite, right? And then we return. Return left min, it shall be the infinite. So we should take no dot val, right? So when this one returns, shall be no dot val. No dot val, no dot val. This is the same. Huh? What is this? What is this nonsense? Oh, you didn't run it. Dude, you did not run it. Alright, I don't know what to say, man. You did not run it. Come on. Come on, you're better than this. Mm-hmm. I think it might be easier to do it the other way. I don't know. Kind of a shame, kind of forgot how binary search tree worked. Yeah. I mean, seriously, if we do the other way, no, I think it should be the same. Like, how good can you be? Without list, let's see. You have to record the previous node. You do this, and then you say the previous node. You set current value. You set previous node. No, I guess it's I mean, we have to set something as self, so that's fine. All right, so we done, right? We've done this. All right. Let's do the real challenge here. All right, so these are timed out. It's okay. That's okay. So the first method is going to be using sorted list to reduce BFS as the base method and use sorted to reduce the search space efficiently. Now this is the second time in a row that we have seen the application of sorted list as a way to reduce search space. This is owing to its fast indexing and removal while maintaining the sorted order of the underlying list. It's just a wrapper of a cleverly implemented self-balancing, right? It's a self-balancing binary search tree. All right, what do you say from sorted list import? Actually, I'm not sure. What's the API for this? I think it's just sorted list. Wait, hold on. How do we do this? From sorted containers. From sorted containers, import sorted list. Okay, so this row seen, unseen, unseen, right? Unused rows. How about that? Unused rows. Right, so this will be sorted list range n. Okay, and now we'll do a sorted unused columns. That shall be n. That shall be n. All right, and then BFS. Oh, it's not a difficult BFS. Q. Right, we're gonna start from 0, 0, and steps equal to. What do we call the steps? Well, this is the first step, right? It's the first step. And then say while q temp for ij in q, if I equal to n minus 1 and j equal to n minus 1, return steps plus 1. Hold a second. Do we return steps plus 1? What if we have a single 1? No worry, all the zippers are closed. Because, well, steps is 0 to start with. So I think we should do 0 here. So now you visited. Right, you visited this, you add a step. Okay. Otherwise, we shall check, right? We are at ij. We shall check on the row which one has not been done yet. So we're gonna do I range. right, we're going to do I range. So in this range, we pick all the one that has not been visited, we put it in. So for k in unused rows, I'm at ith row dot I range from the start shall be j plus 1 all the way to j plus grid ij. But of course it cannot be too big, so we do n minus 1. So these are the unvisited k's. So for each of them we say temp dot append ik, okay, and then unused rows I dot remove k. So we've done all of those. Now we do exactly the same thing for the columns, right? For k in unused columns j, this is going to be I plus 1, I plus m minus 1. Then we're going to append k, right? And j. And then j will remove k. So once we're all done, q equals temp steps plus equal 1. Do you want me to not talk? I'll watch this. Don't worry. You relax. All right, this is not working. What the hell? All right, something is not right. Okay, I need to figure out something is not right. Okay, I'm not sure what goes wrong, man. I am not sure. I am not happy either. Look, 001, 002. Why don't we go to 003? Like, what happened? Dude, what happened? I don't know, man. Hold on. What's this value? This shall be 3. Shall be 4, right? Oh my good. It is 3. So I have +1 here. Oh my god. Yeah, that's my bad. Okay, so at least we solved the one issue. That's good. And then we have index out of range. Funny. Is with this self.parent. Huh. Is the union part, right? Wait, what did we do? What did we do on the K? That it's so unhappy. Okay. 02. K is 3. Should be fine, right? 0, 1, 2. Wait, hold on. We are printing 0, 1, 2, 0, 1, 3. And zero, 2, 3. What? I am not sure what I'm looking at. Union. K is 3. 0, 1, 2, 3. 3 shall be fine. All right, let's try handle that part. See, where do we go wrong? A 4. We have a 4. We have a 4. Somebody get a 4 in. How is that even possible to get a 4? I have a minimum. I have here. How is it possible to get a 4? K is 3, and then we union. All right, so first of all, this is not right. This should be fine. Maybe that's the reason. That should be fine. And it's the same, but a slightly different issue. Where does the 4 come from? It doesn't make any sense, does it? No, it does not make any sense. I don't have a 4 laying around. And it's calling from here. Right, so we're at 2, 3. 2. The column is the second one. Right, K is 3. And then we union 3 and I. I'll get down to the bottom of this. This is ridiculous. We're union 0 and 2. Okay, union 0 and 2. Now we find 0, which is not equal to. So we find 1, which is right. And then we'll find 2, which is right. Right, there's a pxpy shall equal to. Where does this 4 come from? Hold on. Well, so that's not going to show anything. That's not going to show anything. It's coming in 1, 2. Hold on. Parent. So 0, 2 find is 1, 2. Parent is 1, 2. And now I call the find again. Where does this call come from? Maybe it's calling this one more time. I don't know. Because that's the only possibility we can have. All right, how about this? We say row start. We put it out here, so we only do it once on the outside. And then we put a row start here, okay? And we do the column start. And we do the column start. Nope. It's this, j plus 1. Aha, I see. I put a j at a certain position, then it doesn't go. I see. Now I see why. Okay, that's fine. What we need to do is put a minimum here as well. Dude, minimum everywhere. N minus 1. Right, and then this is the same thing. We have to minimum this. N minus 1. What? Oh, it's this thing. Minimum, wrong place. Minimum here. There you go. Minimum here. Minimum this and this. There we go. Oh God. Oh dear Lord. The hell happened? Which one? Okay. This one. Alright, what happened? So we start from here, okay, and then we say, well, find this 1, 2, and this is 0. All right, so this is 0. So we go to the 0, and then we try putting 0 in this position. I cannot go, right? I cannot go. So I stay in the same position. I stay in the same position. And this will stay, probably also stay, like you're here, okay? You're here, and you try to go, but you cannot go. Huh. Maybe I shall do +1. What do you think? What do you think? +1. Then we don't mean it. We just go for it. And then I can cause this whole thing to collapse, right? We won't move forward. We do +1. So I allow myself to be 1 out. And then this will always be the largest, bigger than what this can be, right? And this one will not get out. Okay. Whoa. Took a lot of efforts, man. Really a lot of efforts. But I think we have something here. Yeah, Union Find is very smart. Extremely smart. Damn, extremely smart. But say note that we have to set DSU. We have to have one more position in DSU. This is important to handle cases where a 0 cell happens at the edge. Not sure if I understand in the future, but this is important. Okay, let's submit this. Did you record the time, the previous one? I did. No way. I think I'm either wrong or something. It got stuck. Oh, probably one of... Damn it. Some edge case. Okay. Okie dokie, okie dokie. Okay, we have some edge case we have to deal with. What do you say? The suspicion is still 0. Okay, so how about we still do this and then we check 0 separately, right? How about we say if grid ij is equal to 0, then we just continue. Because when you hit a 0, you really cannot move. You cannot move forward. And then we, oh my god, I'll have to go back to do this. this is going to be this, and it's n minus 1, right? And this is going to be the minimum of this, and n minus 1. This work? Oh, of course, this is m. My bad. Nope. For whatever reason, this is not working. Alright, we have to check. DSU, what type of trick did you use? That's slightly different, right? Let's see. Row dot find column is smaller than the end. We'll take the next one, and then we will union it. Yes, we've done that. And then we append. Go back up. And do it again. Go back up and do it again until we hit So okay, so let's modify it. Here's what they say. Instead of doing this way, we'll always check. Okay, so always check for the current largest while used rows I dot find j current. Right, if this is smaller than minimum j plus grid I j plus 1 and n. Actually, it should be this. Right, if it's smaller than this, then we can say k equal to used row I dot find j. Okay, dot find j. So this is +1. This is the best, right? The best that we can do. And then we can call this, and then we union it. So once we union it, we'll do the next time, we'll point into a bigger one, right? A bigger one. And then because we need the +1, so it has to be smaller than what we can get, the maximum we can get. So when we +1, then okay, so we'll do that, and we'll do this. So this will be column, right? So this will be columns j dot find I smaller equal to I plus this m minus 1. So k equal this plus 1. And this is going to be k and a j. I'm going to union it. This is still correct. Used the implementation from. I hope it's correct. I do think this is a much smarter method. Regarding how to find the next index for each row and column. Yeah, that's what we do. So the one I do is not correct. So what I think is there's still there are still, how should I put it? There are still positions that I'm going over and over again, because I'm giving myself a range. I just say I'll start from whichever and I'll go through everything. But you're not taking advantage of Union Find, because it might happen that the position that you start with, like the next position, the positions after the position you have started with, have been visited before. Yes, exactly, because each position might be visited horizontally or vertically. You can have a position horizontally, right? You say, okay, this is the first not visited position, but to your right, some positions might have been visited already by something going vertically. And if you do that again, then you are, that's not right. Because we're doing row-wise, and the row and column are separately. So if something is visited column-wise, it shouldn't matter, right? It shouldn't matter on a row. This one is just guaranteed every time you find the next index is the biggest one, right? Is the one that you haven't visited yet. The biggest one you haven't visited yet. And the previous one, you cannot guarantee that. You can just guarantee the biggest one given j+1, right? And maybe I see. Yes, I see. So it could be something like this, right? It could be something like this. You have a grid, right? Da 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 da. We hit this and then we go this. So these are visited. And then from here, da 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 da, you hit here. And then you say, I'll do j+1, which is this one, and I'll go through this entire thing. But these are visited, so you shouldn't visit them again. My original method ignores this. I just go every single one. But in this method, once we hit here, immediately jump to the end. That's why this one works. Yeah, you just have to keep checking this. Yeah, these are good check. Good check. I think this one's faster. It's definitely faster. Yeah. A lot faster. This is a great solution. Oh my god. All right, line sweep. I don't want to do line sweep today. It's already 1 hour. Man, this problem is hard. Huh. We accumulated a lot of test cases. That's good. So we still have one more to go. I can't read it. No. I don't want to read it now. Yeah, I'll deal with this tomorrow. Yeah, and this is not for segment tree. Man, how Union Find. Union Find. I mean, the reason we didn't do any of those is because I just thought segment tree will work, which I think it should. I think it should work, segment tree. Technically, segment tree is also OMN log, right? It's the same complexity as this one. So it shall work, but it did not in certain test cases. All right, anyway. I'll stop right here. I will continue tomorrow with the last method. I'll see you guys tomorrow. Adios.